an honor to be here at the RFIC Symposium among innovators, pioneers, and brilliant minds that are changing the future of technology. Today, I will be speaking about the convergence of AI and connectivity, and the critical role that RFICs play in the future of the world. A future where data is abundant, access is instantaneous, and intelligence is everywhere. The title of my talk is Next Generation RFICs, Redefining Data Centers and Wireless Network for the AI Era. We are at the edge of a new technological revolution, and what we do as RF engineers today will shape what the future looks like in the coming decades. RFICs are not simply components. They are the foundations of these intelligent systems. The breakthroughs of our tomorrow's AI, autonomous systems, real-time language translation, immersive AR, rely not just on the better models, but on faster, more secure, and ultra-reliable access to data and processing. AI is fundamentally changing the game, demanding speed, massive bandwidth, low latency, and reliable connections. RFICs are not just part of the ecosystem. They will be foundations to this system. They will enable access to spectrum and also connect edge to the cloud and do all that with the constraints of power, size, and cost. We're heading into the world where everything is connected. Cars, homes, factories, even our own bodies. We're looking at smart cities where all the technologies and devices are connected and interconnected. And these connections are provided with wireless as well as wired connectivity, 6G, 5G, sensing communication. They will be accessed and they will be provided to edge processing. These edge processing are the brain that have the AI and artificial intelligence to be able to provide the real-time kind of solutions to the system and keep this intelligence ongoing. At the higher level, there will be also very massive processing at the data centers, and this edge processing, the local edge processor will have access via clouds to this data processor so that some of the less sensitive and less time-sensitive applications can be managed there, trained, and provide the intelligence as a whole to the entire world and cities. So in the future, sensor devices will become omnipresent. We're already talking about 1 million devices per kilometer square. This is a staggering number. This is way beyond what our network can support today. And the challenge is not the capacity. The challenge is also with the complexity, managing and processing this data at this scale. Now, with 20.4 billion in sensor devices and reaching to trillions in the near future, the scale is changing and it's shifting. And as the scale changes and increases, so does the demand for high performance and high efficiency RFICs. RFICs are required to be able to move the data and get the data from sensors and move them across networks through different kind of standards, including cellular, Wi-Fi, WPAN, satellite. And therefore, they are critical to this system. And they're not only doing that, they're doing it while they have to maintain performance, low latency, as well as the efficiency. With this kind of systems and this interconnected world, we require solutions that are very agile and in their interoperability. Now, for example, take autonomous cars. The system in the autonomous car has to be processing and managing a huge amount of data that's collected from all the sensors, including radars, LiDARs. And this has to be done very quickly and in real time to be able to manage the safe driving. These sensors are basically, the data from these sensors are seamlessly in communications with the car, and they enable the car to be understanding its environment and be able to make very, very quick decisions. This is not just about cars. It's about drones. It's about factories, robots, and the RFICs play a critical role with this intelligent system because they keep the data path going. So within this intelligent world, there are different categories and different technologies. It's not just this world does not depend only on one technology. For example, wireless with all the standards as well as devices that support wireless, cellular, Wi-Fi, WPAN, fiber optics that basically enables the infrastructure with the data center, within data center, outside data centers, smart cities with all the sensors and MEMS that are used in that smart city, including smart watch, smart cars, smart appliances, as well as data center. Again, all these technologies have to be present, and they have to be optimized, and they have to be working together in a unified manner. And what is common in all of them? They all require interface to the real world, and they all require high-performing, high-efficiency RFICs and analog with different requirements, but they all require RFICs. Now, AI technology is a very hungry data technology, and as we move further, it will require even more data. The more data we feed to it, the better performance we get out of it. We have been demanding data, and the network has been providing more and more data from the start and beginning of 1G in 1980s all the way to today, that we're talking about 5G, and we can support about 1 gigabit or even more data rate today. And with that, we have had to move from lower frequency band to higher frequencies, going even into millimeter waves in FR2 in 5G for advanced 5G to be able to support the capacity that's coming with all the applications and need of the network and of the environment. Today, just with the fixed wireless access and mobility, we're almost at the limit of this capacity. Going forward, as we advance in AI and more applications of AI come along, there will be even more and more capacity demand. And that's why 6G will be going to even higher frequency. The mid-band, which is today at 3 or 4 gigahertz, will be moving to 7 to 20 or even 25 millimeter wave. And this will basically enable the support for the huge and explosion of the data. Now, as we go to higher frequency, the demand for RFICs that can support these applications become higher and higher because we need to address the performance. And even though it's challenging, analog and RF are the only way that you can support these high frequencies. Now, with all these challenges and the demand for data, we are already putting a lot of pressure on the network. Our networks today need to be upgraded. They need to be able to support multi-gigabits of throughput, tens of gigabits of throughput and more. We do need to have symmetric sort of bandwidth because so far most of our applications have been downlink-centric. But we need to actually be able to have the same sort of speed on the uplink as well for applications, especially the real-time applications. Low latency becomes very critical for some of these applications, including autonomous driving, very smart driving, as well as robotic surgery, and many applications that are very time-sensitive, and they have to be instantaneous decisions-making. These would be in the range of 20 to 30 nanoseconds. The system have to be very optimized to be able to support a huge amount of data and do it very efficiently and fast. With all that, and all this expectation, the network still has to maintain low power consumption. It's not just about wireless or devices where you have battery operation. It is also about even data centers. You keep hearing that data centers are having challenges with thermal issues. And as you put all these GPUs, et cetera, the thermal impacts the performance. And not only that, also the green energy. They don't have enough sort of energy and electricity to support all these data centers. Let's move to the global connectivity. So far, the focus has always been on terrestrial. Since a few years ago, there has been a huge advancement in satellite communication by rocket and space companies. So now we can get broadband access in the Ka and Ku band from satellite, from LEO satellites. And we're also starting to see direct connection from satellites to our devices, which is very important for emergency and also be able to be accessible no matter where we are. Going forward, satellite will play a key element in our connected world, and they will become integrated with terrestrial. There's a lot of effort in trying to make sure that the connectivity, global connectivity becomes sort of integrated, and satellite will become part of it so that you can make the world even smarter and more accessible. And these satellites will require RFICs that can tolerate extreme conditions and that can also support phase arrays and beamforming, which are new technologies to be able to access the devices as well as be able to manage the capacity. Now, why are RFICs so vital? Because of the physics. RFICs deal with physics. They can interface to the real world. They can manage the noise, messy environment, provide precision, and that is really the main way of being able to make the connection and interface to the world. Digital is powerful, and it deals with bits, but at the end of the day, it has to work with the analog and with RFICs to be able to interface the world. RFICs will be the bridge between digital and the physical world. In the future, it will become more and more important to have hybrid design, where digital, RFIC, as well as the algorithm and AI play together, and they are used together to provide the best solutions that are more intelligent. So we bring the precision and performance of analog together with the robustness and flexibility of digital, with the intelligence into all same design to ensure that we end up with a robust design and we have the best of the two worlds, which is precision, performance, as well as robustness. Talking about all these technologies, future is all about innovation. We're entering an era that will keep moving to higher and higher frequencies in many different applications. Again, even our mid-band is moving from 3 gigahertz to 7 to above gigahertz, and we need to start thinking differently, and we need to start innovating at all levels. As we go to higher frequencies, we can't be doing designs in isolation. We can't be designing a power amplifier separately, or an LNA separately, or our package separately, because every little thing at high frequency becomes important. The parasitics in the package and on the module will become important. So at radio architecture, silicon architecture, design, and every level we have to be looking for innovations, as well as package and separate. We need to think about how we partition our design. Are there things that we can actually do better on the module in the package because it makes it simpler, more efficient? And this is not limited to the design. It's also about deployment. The deployment in this frequency are very different from what we're used to. Focusing on millimeter wave devices, again, we're talking about these tiny antennas because of the short wavelength. I mean, it has its own challenges. The range is a problem. Obstacles are a problem. Penetration is a problem. And the way that we're used to design and deployment in low frequency would not apply here. So we need to be thinking about a distributed kind of system where we have many of these paths, including PAs and LNAs with a large number of antennas. These are the beamforming arrays that we're talking about. And because now we're not putting all the pressure on one device, we can actually have this integrated. Even though it's higher frequency, we can bring the integration of PA and LNA into the chip because we're relying on the full system, the antenna gates, the number of antennas that provide the performance in this area. RF sampling, direct sampling, remain to be an area of very much interest because no matter how high of frequency we go, we would love to have direct sampling and try to make it work at higher and higher frequency. Today, there are solutions, for example, what Xilinx AMD has with their DFE RFIC that has a large integration of ADC DACs in their system along with processing. This can go up to 7 gigahertz frequency, and they can provide, ADCs can do 5.9 gigasample per second, and DACs can do 10 gigasample per second. However, now, as I mentioned, the mid-band is moving to high frequency too. So now we need to be thinking about 7 gigahertz all the way going to 20 and beyond. So we need to make sure that this ADC and DACs are designed so that they can support 15 gigahertz and they can provide performance. And one of the things that is happening in parallel is the process nodes that are improving. So as we go to 3 nanometer, 2 nanometer, we should be able to shrink and bring more of these ADC DACs and keep doing innovations. And we're hoping that this can support many different applications. So ICs will have multiple and many of these ADC and DACs. Software-defined radios will become more common, will be used more, and they start becoming more available in commercial. We've been talking about software-defined radios. We've been trying to build software-defined radios, but the challenge has been the cost, power consumption, and the overhead that they bring. We want to be able to bring solutions together that can address multiple frequencies, multiple applications, and these will start becoming more reality. If you look at what I showed on, for example, on the DFE in the previous page, on the left-hand side, you can see it here too. These already have a large integration of ADC DACs. This will keep advancing. We will be able to bring more processing. We will be able to do higher, faster sampling, integrate a large number of them in very in the geometries that are 2 nanometer, 3 nanometer. And we should also be able to do innovation and bring more integrated front end for mid-band, low-band, as well as the little tiny antenna arrays in millimeter wave. And this can form together a solution that can address multi-bands of millimeter wave and many different bands at the lower frequency. Again, this will be happening over time, and it relies a lot on the process nodes that are advancing, becoming more mature. Substrate and package become very important because, again, we're not trying to do everything on the silicon. We will be using, we will be thinking about and doing some innovations as where we put, for example, filters or a combination of how we partition the architecture. There are many areas for innovation, and I actually saw papers that they got awards, and it looks like people are already working on that. So some of the areas that I can highlight, and many of you guys are aware of, is we all know we would love to have linear wide-band amplifiers, whether it's in the power amplifier side or in the low-noise amplifier. We would love to be able to cover a huge bandwidth and maintain the performance because we don't want to sacrifice performance. Power amplifier that can be linearized, that can support very high linearity. Multi-band RF front ends. We have devices today that are using many different filters, antennas. So ideally, we want to bring them all into one sort of solution where we can do a tunable antenna, low-loss filters, that we can basically tune and selectively and dynamically adjust based on the application. massive MIMO and phase arrays, both in mid-band as well as the phase arrays in the millimeter wave, are becoming more and more important. Power consumption remains to be one of the areas that we need to be optimizing, as well as the performance and selectivity. Now, many of these arrays require extensive time to be able to do calibrations, make sure that PAs, for example, have the phase alignment as well as the amplitude to be able to perform and deliver the performance. This, if we can work on solutions that reduces this time or basically get rid of this calibration, it can do auto-calibration to tune and calibrate these devices or these arrays. That would be something that would be very, very helpful. As well as linearity. Like power amplifiers today, we're using DPD, we use envelope tracking and try to make our power amplifiers linear. When you have a large number of amplifiers, power amplifiers, it becomes a challenge. You won't be able to do as much as you can do on one PA. Going forward, the transceivers need to become more smarter. They need to be able to basically automatically improve performance, and that means bringing more digital and AI into the picture so that you can calibrate, you can actually tune your gain, etc., for the best performance. And eventually, the synthesizer and PLL, it's an area that as we push to go to support higher modulations and higher frequency and wider band, we need very, very powerful, low power consumption synthesizers that can support low spurs, that can go to the very low jitters, and that also remain an area of interest. So I mentioned, doesn't matter what we do with the design, at the end of the day, when you go to higher frequencies, you're going to have to deal with the physics and challenges of the physics with short wavelengths that get blocked, the range is shorter. So the way that we should be looking at the future is not just trying to maintain the way that we have been thinking. We have to think differently. We need to start thinking, okay, what makes sense in, for example, deployment to make that possible? And that, for example, in millimeter wave, would be something more distributive. It doesn't mean that you cannot deploy. It means that you have to be doing it differently. You have to have devices that are very low cost, very easy to install. And they can make sure that you get your coverage of working with the base station. Once you have this ability, once you have these devices, you have optimized deployment, etc., we would be able to have digital twins. You will see a lot of different digital twins, meaning that you can replicate a physical environment identical to that on your monitor, and you would be able to see exactly what's happening instantly. So it's a replica of your physical environment, and that improves efficiency. That makes everything go faster and smoother, because you can do all your simulations. For example, if you're trying to do deployment, you can actually do everything on that monitor, and then go and deploy it in the actual physical environment. Now, this requires a huge amount of data, a lot of sensors in the environment, a lot of data back and forth, and instantaneous, so very, very low latency in order to be able to make sure that you're actually seeing exactly what's happening out there. And these require basically RFICs, and this requires connectivity. That, with it, has to come high-performing RFICs. An example of what basically we have been doing at Movandi to bring, to address some of the challenges is, and bringing this new methodology into the picture is smart repeaters that we have built. These are solutions that can enable deployment of millimeter wave. It can bring the cost lower. So we are using our analog RFICs antenna array. We are also using an engine in addition to that will do some of the digital work and smartness to the limit that you can actually make this device smart enough without adding overhead or latency to the system. And these devices can make a big difference in the cost of deployment. Now, This is the picture of how these devices can help. For example, if you look at this small section of the city, there's the base station with millimeter wave. Many obstacle buildings that will prevent the coverage to be provided in the whole environment. Now, with these devices that are very easy to install, under street lights, they don't need fiber, and they're low cost. We can ensure that we extend the coverage. These devices can be cascaded, they can work in a mesh network, and they ensure that not only you get the coverage, you also can enable intelligence from base station back and forth to these devices and improve the environment, and that is via the API interface to these devices. So this is an example of what recently was done. We built this system, basically it's our technology that we use with Kyocera and KDDI, and they have built these devices you see on the top in the pink area. And they deployed it in Shinjuku area, which is a very crowded area on the streetlights. Without the repeaters, they were getting only 30% coverage in this area. You can see at the bottom on the left-hand side. And after deploying these repeaters, they basically recovered almost everything, 100%, with very good throughput of higher than 1 gigabit per second. So if you have smart devices, you go there, you can see your device can get connected to the system. And it's using mesh network so that it will provide you with the robustness of the system. This can be used for FWA as well, and in the future, AI can be sitting in the base station and make sure that the system is even smarter. Now, the future is intelligent, and intelligence is ambient. I mean, sensing, communicating, all around us. And RFICs will be playing a big role, and they're fundamental to this system. Intelligence will not exist without connectivity, and connectivity will not exist without the RFICs. And that's why we need to make sure that we work together, we keep innovating, and provide solutions that can enable the full potential of this intelligent world. Thank you.